Okay, so good morning, everybody. Okay, so please tell me, do you hear me?
Good morning, yes.
Good morning.
Thank you. All right. Okay. So I think how many people we've got at this moment? $17 only. Okay. Too bad. All right. So welcome again, and as I said previously last week, we'll be continuing the problems or the problems with bipolar transistor amplifiers. In fact, electronic amplifiers based on bipolar transistor. Last time, as I remember well, Jakub asked to make some example based on the PNP transistor. Yeah, that's right.
Yes.
All right. So I think we can start with that type of exercises, which based on PNP transistor. However, at the end of the last classes, I told you a little bit more about the designing of the amplifier based on the transistor. So maybe it is good idea to try to make the example based on in fact designing such amplifier based on PNP transistor. I will show you a different way, different type of examples. In fact, it is opposite to the example what we have on the classes. We haven't any values of resistances, and we have to build the amplifier based on PNP transistor. Okay, so this first example, it is like that. Okay, let's design for example PNP bipolar transistor based amplifier, the amplifier. Working at a type class. What does it mean? The first thing, what does it mean, the A-type class? A-type class, it is the class where where through the transistor, anytime we've got the DC current. DC current is passing through any time, and if we plug in the input signal, which want to be which has to be amplified, in fact, this DC stable, fixed point of the current which is passing through by the transistor is starting to change or fluctuating according to the input signal. That's the A type class amplifier. Yeah. All right. So first of all, okay, we've got the sentence. Okay, we haven't any, in fact, the input values. First of all, as you remember from the last classes, we've got the PNP and NPN transistor. PNP looks like that. The arrow at emitter is entering to, as a symbol, is entering to the emitter, in fact. This is the collector, this is the base. Okay. What about the polarities? The polarities of the emitter, collector, and the base is completely opposite to NPN transistor. What does it mean? It means that the emitter should be at the higher potential than collector and then base. So we have to apply correctly the input or supply voltage to reach that conditions. Yeah. The highest potential should have the emitter, and the base and the collector should have the lower than emitter. Okay, so we've got the emitter here. If you remember well the last example, which was the last week, at emitter we have some resistor RE. We can put it here, the emitter resistor. Okay, it is good idea because this is the negative look back. In fact, for such amplifier, that means that type of amplifiers are so much more stable. In fact, however, I don't want to talk about a lot about the stable of the amplifier because I think you will have the special course, I think, electronic circuits about it. So it doesn't matter. Okay, so this point should be plugged into plus VCC, the DC supply voltage. Okay, we've got the collector. As you remember, in the collector we have to put the RC resistor, and what else is going to the ground. Okay, so the positive potential is here, the ground is here. So as you see, in fact, the emitter will have the higher potential than collector. Yeah. What about the base? We know that between the base and the emitter, we've got the VBE voltage drop. Yeah? For the silicon transistors, it is from 0.6 to 0.7 volts, yeah, typically. Okay, so as you see, because this potential should be lower than the potential of the emitter, so the voltage drop of the VBE should be assigned like that. Yeah? The arrow should be here. Okay, we've got it. All right, we have to polarize. We have to polarize the base. How? Look. What are the currents? How the currents should flowing through the PNP transistor? Opposite to the NPN. So this arrow showed you that the emitter current should going to the entering to emitter, and this current in PNP transistor is in fact divided. by the base current, which is leaving the base, and collector current, which is also leaving the collector. Yeah. So as you see, the emitter current is passing through here and is split out here to the current IB and the current IC. Okay, so as you see, we have to put it here, the resistor, which will limiting the base current, and connect it to the ground. That's all. This is the RB resistor. Okay. So where's the input signal should be supplied to our amplifier? To the base through the capacitor, where we have the output signal from the collector. Okay, we can take it from the emitter also, but typically it is take it from collector. All right. So we've got it. Maybe you remember from the last lecture, to get the A-type class of the amplifier and define the working point for the transistor, which means we have to calculating the current IC and the voltage drop between the collector and emitter. What should be the voltage drop on the collector emitter? Do you remember?
Here minus 0.7 volts.
No, between the collector and emitter.
Oh.
Between the collector and emitter. Okay. Maybe you remember this. This plot. This is the relationship between the collector current and the voltage drop between collector and emitter. For some base current, which is constant, this function looks like that. Yes. And somewhere the voltage drop between collector and emitter cannot be higher than the VCC. Yeah? This is not possible to get a higher voltage drop than the power voltage supply. So here we've got the maximum value of UCE, and this is the VCC, in fact, value. And to get the A-type class amplifier, the DC current of the collector should be around the half of VCC. Yeah. So this point, it is our UCEQ. This is the working point for the transistor, which gave us the ICQ current point for transistor. This is the working point for it. And as I said last time, input voltage, which is plugged into the input, changing the base current, and the IC current is starting fluctuating according to the input signal. And this point is start moving on this chart, according to the input voltage. So as you see, this is the A-type, which means that anytime the current ICQ is passing through, and both sides of the input voltage value, it means positive and negative pulse of it, is lie anytime on this linear part of this chart. Okay, so as you see, the one condition is to build such amplifier, we have to get around UCEQ equal the half of VCC. Okay, so this is for us the first information. All right, so we can make it in that form. We have to design it. So the question is, what the VCC voltage we've got? It depends on us. Let's say we've got the voltage supply, for example, 12 volts. We use some voltage, maybe not the reference voltage circuit, but the stabilizer, voltage stabilizer, and we fixed the VCC value at 10 volts, for example. Yeah. Okay. So the first thing, the VCC for us is at 10 volts. It depends on us. Yeah. We choose 10 volts. Great. So to get the A-type class, we know that voltage drop UCEQ between the collector and emitter should be around the half of VCC. Okay, so what about the voltage drop on the RC resistor? We have the output. Let's say the VRC, it is 10. Let's put it here, the 5 volts. Okay, so the UCEQ should be equal, we don't know, it depends on us. We've got also the voltage drop on RE. Okay, so we don't we can choose the so huge VRE voltage drop. Yeah, why? Because we wanted to get the UCEQ around half of VCC. Okay. Oh man, sorry. And it depends on us how many voltage drop we choose. So if we put it here as a VRC 5 volts, so we have 5 volts. We have to divide it 5 volts between the UCQ and VRE. Okay, I think it is a good idea to put it here the 0.5 volts for the RE, and UCEQ will be equal 4.5 volts. Yeah, so the 4.5 volts is around the half of VCC. Great. What about the voltage drop on the RB? It is here. We've got it. Great. Next thing, we have to assign the currents in our circuit. So as you see here, we've got the emitter current. This current is entering the emitter through the RE. Okay, everything is okay. We've got the current IC, and this current IB is passing through by the RB resistor. We've got every voltage drops in our electronic circuit. So what we can do in the next step, we have to calculating something. We have to find the values. First of all, we have to choose the transistor. Why? Because we have to find the beta for calculations. So that's why we have to go to the data sheets or catalogs and choose some transistor. I can suggest that, because this is the rather the audio amplifier, very simple audio amplifier with no so huge the bandwidth, in fact. So typical the BC type of transistor is enough. Maybe it could be the BC 857A. What is the letter A? We've got the A, B, and C at the end of this the name of transistor, bipolar transistor. The letters at the end show you what the beta of transistor we've got. It means the A, it is rather low beta values. B, it is in the middle, and C, it is a very huge beta value. It means, for example, A, it is around 100, 150. B, it is around 300, and the C letter, typically it is even above 800 of beta value. Okay, so what we have to do in the next step, I'm welcome you to the, where it is. Where it is. Okay, here it is. To the LT Spice. We are going to the LT Spice. And let's put it here, this type of transistor. We have to choose. Do you see the LT Spice desktop?
Yes.
Okay. We have to choose the PNP transistor. Oh, I've got it. I have to change its the place of it. So I have to maybe rotate it here, rotating it. Okay, I've got it. And the right clicking on the transistor, we've got the button as the pick new transistor. If we've got it, if we have to find such transistor. Let's say 578. Okay, I've got it. Look, this is the model of our transistor. When you take a look at the parameters, you'll find the parameters which is called the BF here. Do you see it? Do you see it or not?
Yes.
Oh, great. So BF, it is the beta. So the beta for this transistor, it is 161. So we know that the beta is equal 160. It's enough. Okay, so we've got it. Okay, let's coming back. Let's coming back to our calculation. So we know what the beta is for that transistor. Okay. So first of all, let's calculating such resistor. However, we can make it before we don't choose the collector current. It depends on it. It depends on us. It depends on us. So the question is, because we've got the 10 volts of power voltage supply, so what you think? What the IC current you are thinking that is good to put it here? We know that VRC, the voltage drop on this resistor, it is 5 volts. Yeah. In fact, the question is not exactly what the value of the current, which means the number of the current. Much more important is what will be the prefix here. It means it will be the amperes, it will be the milliamps, or maybe microamperes. Okay, look. Typically, we don't want it to get so power consumption for such amplifier, low power amplifier. So we are rather thinking that the few milliamps is enough for the DC current which is passing through by the collector. Yeah. Look, if you put it here, the 5 milliamps, what will be the RC value? Because we choose the voltage drop on it 5 volts. 5 volts over 5 milliamps, it is 1 kilo ohms. Yeah. So as you see, it is very good, I think, way to put it to choose the IC current. So 5 milliamps, it is not so huge value. Yeah. So the power consumption by that amplifiers will be only not so huge. It is 5 milliamps, that 10 volts.
I'm sorry.
Yes, Jakub?
Why do we need RE resistor?
Why? As I told you, the RE, in fact, this is the negative loop back for the amplifier. It is for that. Why? Because this loop back working in that form, if the input current, base current are changed, also the emitter current, it is changing too, according to the beta value. So as you see, if, for example, something was changed in our electronic circuit, like the temperature, for example, is going to increasing so much, what does it mean? What happened then? The resistances are changed when the temperature is going up. Yeah. And if the resistances will change here, for example, let's say it is going down. Yeah, something was happened and this resistance is going down. It means that the voltage drop on this resistor is going down too. So if if it will happen in that form, I think, yeah, when the resistance is going up, the temperature is going up, the resistance is going up too. Sorry, when the temperature is going up, the resistances of the resistor is going up too. So the voltage drop on this resistor will be going up. Yeah, so if it will be going up, it means that for stable UBE voltage drop, the voltage on the RB should what? Should be changed. Yeah, should be changed. So will decrease. So it means that the current are changed of the base. If the current will change, it also the IC current will be changed. Yes. So if it's true, so the emitter current also. So what's the case of it? This changes. It means that if the resistances will change and the current want to passing through a little bit low as a consequence, the emitter current is going up too. So as you see, the temperature changing the resistances, the current should going down. In fact, because this resistance is increasing. However, as you see, due to the invert feedback loop, the current, the beta is increasing because the voltage drop on it is going up. So it make that the current IE is increasing. So as you see, even the temperature will change, the current IC, as a consequence IE also, is also
long today exercise will be?
we've got in fact 4 hours, yeah.
So if it will
If you
throw
will
us
make some
again
break,
after,
okay.
Okay.
If we will make some break, then I will try to connect it by that domain. Okay. All right.
Okay.
Okay. So let's go further. We've got the current IC current, which is the 5 milliamps. Okay. So what will be the RC? RC, it will be, according to the Ohm law, VRC over IC. So this is 5 volts over 5 milliamps. It is 1 kilo ohms. So we've got the first resistor. All right. What about the RE value? Okay, we choose that the voltage drop on it should be 0.5 volts. However, we have to find the current IE. As you know, the current IE, it is in fact IC plus IB. Yeah. We know the IC, we know the beta. So the IB will be equal IC over beta. So it will be the 5 milliamps over 160. And this is equal, we have to check it, 5 milliamps over 160. As you see, this is 31.25 microamperes. Okay, we've got it. We've got the IB. Great. So the current IE, it is equal 5 milliamps IC plus IB plus 31.25 microamperes. So it is equal 5.03125 milliamps. We've got the emitter current. Okay, so the RE will be equal VRE over IE. So this is the 0.5 volts over this value, IE. How many it is? 0.5 over 5.03125 milli. As you see, this is 99 point around 4 ohms. So we've got the RE resistances. Great. Okay, one thing here, because we want to finding the RB value, which is equal VRB over IB. We've got the current of the base, it is 31.25 microamps, and we don't know what is the voltage drop on this resistor. However, we see that the VC, 10 volts, should be equal voltage drop on the emitter resistor plus UBE plus VRB. This three voltage drops should be equal VCC. Yeah. All right. One thing. What is the VBE voltage drop? So what is the base emitter voltage drop for the silicon transistor? It is, as I said, it is from 0.6 to 0.7 volts. We can choose the 0.7, for example. All right. So the VRB will be equal VCC minus VRE minus VBE. Okay, how many it is? 10 volts minus 0.5 minus 0.7. Yeah, that's right. Or not? Okay, so 10 minus 0.5 minus 0.7, it is 8.88 volts. Great. So we've got the VRB. So let's substitute this value. 8.8 volts over IB, 31.25 microamperes. How many it is? 8.8 over 31.25 micro. As you see, this is around 282 kilo ohms. Great. So we've got any resistances. We got it. What else? That's all. So I think we can check it. In fact, our design amplifier based on PNP transistor, we can check it using the LT Spice. All right. So I have to switch to LT Spice again. So this is our transistor. Okay. So very quickly, we have to put it here, the resistances. Okay. We have to find the voltage. Yes, got it. We have to put it here, the ground. And very quickly, let's connect any wires. Okay. Yeah, I've got it. The emitter resistor was equal 99.4 ohms. The collector it is 1 kilo, 1 kilo ohms. And the base resistor, we found that it is equal to 182 kilos. Great. The input voltage, supply voltage, it's 10 volts. Okay, I've got it. And let's check the voltage drops and the currents. So first of all, we have to run the simulation for the transient simulation, of course. Stop time, let's put it here, the 100 milliseconds. Start saving data because we don't want it to observe the we have to observing it for the steady state. So let's put it here, the 50 milliseconds for saving data, and the maximum step time, it is 1 milli. It is enough. Yeah. All right. Let's run the simulation. All right. And let's check first of all, let's check the base current. Okay. How many it is? Do you see it? What is the base current value? 31.24. Yeah. So as you see, it is almost that was calculated. Great. Okay. What about the IC current? Okay. It is here. I will change the color. How many it is? We choose that IC current should be 5 milliamps. In simulation, as you see, it is almost 5. It is 4.95 around milliamps. Great. What is the next current? As you see, it is almost 5 milliamps. It should be higher a little bit. However, if IC is the lower, so if we substitute the base current, it is almost, in this case, it is almost 5. Okay. What about the voltage drops? For the collector resistor, the voltage drop is equal around 5 volts. Yeah, 4.95. Okay. What is the voltage drop between collector and emitter? We set it as the 4.5 volts. Okay. However, as you see, I have to use the reference probe here. Okay, I've got it. How many it is? Oh, it is 4.55 volts. We choose 4.5. Oh, it is around it. Great. And the voltage drop on the emitter resistor, sorry, it is equal almost half of volts. Great. So as you see, it is nice. It works. Let's check what is at the simulation the voltage drop between the base and emitter. We set it as the 0.7 volts. However, as you see, for this transistor, it is 694 millivolts. So it is 0.69 around. So it is almost 0.7. Yeah. So as you see, we've got a little bit the differences in the simulation and of course in the real circuit, and against the what we calculated. It is typical. However, you have to know that if you wanted to build that circuit in real, so we have to choose the correct resistances. As you know, we don't have any resistances. So as you see, as the emitter resistor, which is equal from calculations, it is 99.4 ohms. So as you see, we have to choose and buy the 100 ohms. Yeah. Also here, as the base resistor, it is 282 kilos. So as you see, we have to choose. Probably we will find the 280 kilos, the resistance. So as you see, the current in real circuit will be the base current will be different, a little bit different, not so huge, but a little bit. So as you see, also the collector current will be a little bit different. However, as you see, it works. And as we have running the LT Spice at this moment, I can show you what happened when we plug in the input signal. First of all, we have to put here the capacitors, because DC current cannot passing through to the generator or to the load resistances. This is our output signal and output resistances. Okay. For example, let's put it here, the 10 kilo ohms, for example, and let's choose 270 microfarads of the capacitance. And what we have to get, we have to find some voltage signal, right? Okay, you can check it. We have to click on the advanced, and let's choose the sine waveform. DC offset 0. Sorry, DC offset is 0. The amplitude. Okay, let's starting with the 100 millivolts and the frequency. As you see, we've got the how many? We've got 50 milliseconds. We've got on this of this chart. So how many? 100 hertz is enough. Okay. So we've got it. And now let's delete the last waveform and let's run the simulation. And let's check what the signal is on the input. In real, it is 100 millivolts peak to peak. Not peak to amplitude. Yeah. So peak to peak it is 200. Great. So we've got it. How the voltage of the base, the potential of the voltage potential of the base are changed, as you see. It is starting to fluctuating. 8.8 volts. It was around the stable voltage drop on the resistor. If we plug in the input signal, as you see, this voltage are changed, yeah, due to the input signal. So as you see, we've got the modulation of the base current. We can check it. What is the current change of the base? Do you see? It is also the sine wave from here. Okay. So the input signal, it is here, yeah. And what happened on the output? This is the blue one. Look, the input signal are changed 100 microvolts as amplitude. On the output, we've got the magnitude changed to how many? To the 850 millivolts. So it is nice. We've got the amplification of the voltage and also the current. That's the reason how it works. I wanted to show you how it works, in fact, in real. Great. What about the current here? Collector current are changed too. All right. So I want to show you also that this voltage drop, which was around 5 volts as a voltage drop on the collector emitter, it is here. When we plug in the input signal, this voltage drop on this resistor are changed also. Yeah, of course. That's why we are observing the voltage signal output on the load resistances. Look, this is the voltage on the resistor, and this is the voltage after capacitor. As you see, the capacitor reduce the DC offset, yeah, of the signal. So as you see, DC signal is not passing through by this resistor, yeah, but only the AC signal is going to the load resistances. So that's why, that's the reason, or maybe not. That is the way how we can very simply show you how works the capacitor here. Yeah. In fact, he stopped the DC current flow through it, and we've got the pure AC signal on the, for example, resistances here, or the loudspeaker, for example. Okay.
I'm sorry.
What else? What? Yes, Jakub?
Passive power draw of this amplifier is around 50 milliwatts. How much of this is
50 milliwatts?
How much power? This should use about 15 milliwatts. Because I think so.
DC power. This is the power consumption from the supply voltage.
Yes, 5 milliamps times 10 volts.
Yes. Okay.
Okay. So, but how much power we are putting into load?
Into the load.
Yes.
It depends what will be the input signal. This is one thing, because the power is delivered as is the form of the AC signal. That's right.
Yes.
Okay, this is one thing. And the second limitation, it is the maximum current of the collector and emitter, of course, for the transistor. So you have to check on the data sheet for this transistor what is the maximum current which can passing through by this transistor. That's the limitation here. Okay, great. Okay, so let's increase the input signal amplitude to 200 millivolts. So as you see, we are observing that the output signal is increasing. It's increasing. Okay, and so on. Let's increase to 400 millivolts. Nice. Quite good. 500 millivolts. Look what happened. What happened with the output signal? Do you see it? At this point. Okay. So let's check it. What happened with the voltage drop on this resistor with DC voltages? Here we've got the end of the increasing of our amplitude. Why? Because the transistor is saturated. It means that when I use the mark here, for this point, as you see, the voltage between the emitter and the collector is going to this value. It is almost zero. Last time I told you that the saturation voltage for the transistor, it is around 0.2 volts. Yeah, let's check it, how many it is. Wait, sorry. Okay, let's go to the minimum value. All right, for this transistor, in fact, for the low current, it is not, this is 70 millivolts. 70 millivolts. That is the saturation voltage. What does it mean? It is the saturation of the transistor. The current stopped passing through it. So, as you see, at this point, for the output signal, that's why we've got the cutting of the tip of the sine waveform here, because the current is stopped passing through it, because transistor is, at this point, is completely completely open. Okay, we can check it. We can check it. Where? What about the current? Input current is okay. This is okay. Yeah. Okay. It was here. Yeah. The saturation of the voltage between the emitter and the collector. What will happen when we're increasing the signal, the input signal? As you see, oh, this is it. Here we've got the cutting of the current, and here we are observing what? The changing of the shape of our waveform, sine waveform. Why? In the one case, we are going to the limiting of the VCC. In the one case, we are going to the what? To the saturation of the transistor. So as you see, we can put it here so huge the input signal. Yeah. Yeah. Due to the amplification of the current, and as the consequence the voltages on the output, and the turn off, completely turn off or completely turn on the transistor, saturation of the transistor. Okay, so as you see, for this transistor based amplifier, we can put it here the higher voltage input as, for example, 450 millivolts. Let's check it. Yeah, that's right. 450 millivolts, it is enough for this amplifier. As you see, this is the first, this is the very simple amplifier for headphones, for example, where the input signal is going from some, I don't know, USB recorder or something like that, which is gave us the maximum, I think, the 50 millivolts, yeah, for the maximum loud. So as you see, it is good. It will be working as the headphones amplifier when we plug in here the some music source like some USB recorder or something like that. Okay, so that's the yes, Jakub.
If we would want to control input signal, we could use a simple voltage divider.
Where? Here?
Input, yeah.
Yes, however, everything depends what will be the bandwidth here. However, if we are thinking about the typical audio signals, okay, for this meeting will be end in 10 minutes, okay? upgrade now to remove the 30. Aha, I have to upgrade my Zoom software. Okay. I don't know when I click on the upgrade, everything was stopped. Maybe not. Okay. Do you hear me? Hey
Yes.
guys. All
Yes.
right. So everything is going right. All right. Good. So as you said, Jakub, okay, you can use the typical voltage divider to reduce so huge input signal, in fact, for such amplifier using the typical voltage divider. Yes, I think yes. For the audio signal with the very narrow bandwidth, it will be working. Yeah, it will be working. Great. So as you see, in fact, the LT Spice or Spice, in fact, the software for simulation is so powerful. In fact, the softwares we can choose a lot of circuits and check it is work or not. It is very helpful for designing also. Yeah, great. However, you have to remember this is only the simulations. Yeah. The real world is a little bit different. Yeah. However, in fact, if you will build our circuit in that form, it will be working in real. The current will be also at this range what we calculated, what we are calculating. All right. Great. So I think it is enough about this amplifier based on the transistor. I gave you the PNP PNP example, PNP based transistor example, and what else? I think we can go to the next example. Okay, new share. And where is my? Okay, where's my camera? Where is my camera? I don't see it. Screen. Sorry for the while. Okay, I've got it. Are you still there?
Yes.
Yes.
I will ask you times to time because I don't know what happened with this Zoom. I don't know that will be disconnected or not. All right. So next example. Very quickly. So please tell me. I think you know a little bit about the electronic circuits based on the transistor. Yeah. It is the new knowledge for you or not?
I knew something about MOSFETs, but about bipolar transistors is new.
Okay. And the other people, sorry.
Same, pretty much the same.
Yes, Camille? All right, so the next example. I'm just want to show you that these terms what we had previously, it is very helpful in fact any electronic circuits for any electronic circuits. Okay, let's imagine that we've got the the next type of base polarization setup of the bipolar transistor amplifier. Okay, as you see, this is the what type of transistor we've got here. Please tell me. For example, Camille.
It's the
NPN.
NPN one.
NPN, yes.
Yes.
Yes, the previous one was PNPN.
Yeah, NPN transistor, of course. Why? Because at the symbol, this arrow is leaving the emitter. Yeah.
Yeah, exactly.
All right. So that is the last type of polarization of the base using the two resistances. In fact, it is like the voltage divider here, yeah, as you see. All right, this is the VCC, and we've got the input values like the RB1, it is 50 kilos. RB2, it is 0.2 kilos. RC, it is 820 ohms. RE, it is 500 tens. VCC, it is 10 volts, for example. UBE, let's say this is 0.6 volts. And the beta of the transistor, it is 100. Great. So how we can solve this example? We have to make the DC analysis for that circuit. It means we have to find the ICQ and CEQ value. It means the voltage drop between emitter and collector at the working point for DC analysis, UCQ, and the current ICQ. All right. First of all, let's find the current directions, and it looks like that. As you see, from the voltage supply, the current is splitting in this junction by two currents, first and second. This current is passing through by the RC resistor and is going to directly to emitter. It means that this is to the collector. So this is the collector current. This current is passing through by the RB1 and it is splitting by what current? This current, it is, for example, IB2 current. This current, in fact, is entering directly to the base. So in fact, this is our IB current. So this one, it is current IB1, for example, yeah. All right, so please note that we can put it here, the current IB, because it is not true, yeah. This is not the base current here. The base current is here. And the last thing, it is the emitter current. All right, so now let's draw the voltage drops on any components here. And we've got here we've got what? This is the UBE voltage drop here. UBE.
5 seconds.
Sorry? For the rest people to connecting. So as you see, I think that the pandemic is going to the end because the Zoom is limiting now. So,
I mean, the Zoom support replied to. I don't know if any can you hear me?
yeah.
Okay. The Zoom support replied to someone from Politechnika that the restriction is actually not lifted and never was in Poland, even though it technically was, but it does sometimes cut out. But like, I don't know if you've seen this, but there's this website this app that Politechnika made, vc.
Yes.
Yeah, and so supposedly because they have some licenses that they bought.
I see.
If you do the meeting via this app, it will also assign you a license for the time of the meeting, so it shouldn't kick you out. And they made it like just because of that reason, because of that 40-minute limit.
Okay, I
this
get
is like an official app from Viewer, and you log in with Educacja or something, and you can even see the groups you teach, etc.
Okay, thanks, Wojciech. Great. So I think we will finish this example, and then I will try to connecting using that the Polytechnic, the web address. Okay. All right. So let's continue. This is the voltage drop on the RB1. This is the VRB2. This is the voltage drop on the collector resistor, and this is the voltage drop on the emitter resistor. Great. So typically, how we can solve this circuit? Yeah, we will have to build the equations for this branch, and then we will take it into account the UCQ value because we have to find them. We'll take it in consideration the IC current. However, as you see, we've got the IE also, so we have to take the another equation which consists the current IB. Okay, so let's try to write the equations for it. First of all, let's say the first branch, this one. As you see, the VCC, according to the Kirchhoff voltage law, VCC minus any drops in this branch should give the 0. Yeah, VCC minus any voltage drops should give the zeros. So this is the voltage drop on the RC resistor. It is ICRC. Okay, minus UCQ, we've got it, and minus IE times RE, the voltage drop on this resistor. And this should be equal 0. The next one, for example, we can choose this branch. So this is very simple. This is VCC minus voltage drop on this resistor minus voltage drop on this resistor. And this should be equal 0. So this is IB1 times RB1 minus voltage drop on the RB2. IB2 times RB2 should be equal to 0. Yeah, okay. We've got one unknown values. These are not. This is the RC, IC and IEC and IE. However, as you remember, the current IC, it is the IB times beta. Yeah? All right. Current IE, as previously, this is the IB times beta plus 1. Yeah? Right. And one thing. For this junction, according to the Kirchhoff current law, we'll see that IB1 should be equal the sum of these two currents which are leaving this junction, IB plus IB2. Okay. So that will be the task for you at home to solve it using that equations and remember about it. So please solve these equations, finding the ICQ and UCQ. It will take you a little bit more time and the possibilities to make the mistake or mistakes. However, for such example, we can use the Thevenin theorems. How? Look, this setup I can draw in a little bit different. Why? Look, the problem is with this IB1 and IB2 currents. Yeah, if you will have the one resistor here, there's not a problem because the IB current it is passing through by this resistor, and in our equation will have directly the IB current. All right. So this is the first branch, and look, I can draw the base polarization branch in that way. Yeah, because these points are the same. The VCC and VCC here, it is the same. Yes. So, look, please imagine that this part of our electronic circuit will change according to the Thevenin theorems to the equivalent circuit, like that. ETH and RTH. Okay? This point, let's say this is the A point, and this is one, it is B, this is the ground, yeah, okay. So according to these 2 points, let's find the equivalent circuit. Okay, this is the A and B. Great, this is the RB1, this is the RB2. Okay, so we've got it. How we can find the RTH and ETH for our circuit according to A and B points? Do you remember? How we can find the RTH? What we have to do? Do you remember? Hello? Jakub, do you remember? How we can find the RTH?
We should tie VCC to ground.
VCC, yeah, to ground. Why?
To remove voltage.
Of course, yeah, we have to change the voltage source by the short circuit and the current by the open circuit. Look, this is the VCC here. I can draw it in that form. This is our ground. RB1 and RB2. Yeah, this is the same. And here we've got the A and B points. Yeah, that's right. This is the same. So the voltage source is short circuit And the RTH, this is the equivalent resistance according to the open A and B points. So how these two resistances are connected when the VCC is short circuit?
In parallel.
In parallel, of course. So the RTH will be the parallel connection of the RB1 with the RB2. So this is the RB1 times RB2 over the sum RB1 plus RB2. And if you substitute the values here, we'll get the 5.3 kilo ohms. Great. Next thing, we've got the RTH. We have to find the ETH. Look, what is the ETH? ETH, it is the voltage drop between the open A and B point when we're coming back with the sources. So we've got the VCC here, we've got the RB1, RB2, and we have to find the ETH. Please tell me, do you see here the voltage divider? This is the classical voltage divider. That's right. So please tell me what I have to put it here. ETH is equal, please tell me.
VCC.
Yes. Times the input voltage.
RB2.
RB2, yeah, of course. You have to remember. In nominator, we have to put the resistances where we're observing the ETH in this moment over the sum of the resistances in the voltage divider. Okay, so this is 10 volts times 8.2K over the sum of these two resistances. So this is 23.2K. The kilos will be reduced. So it gave us around 3.53 volts. All right. So at this moment, we've got the equivalent circuit, which is which is, oh sorry, what happened? Which is indicated by this the red dot area. All right. So our circuit at this moment looks like that. ETH, RTH, okay. This is the A and B points. And then equivalent circuit we have to connecting to the rest of our circuit. So what we've got? We've got it. All right. So the currents. And as you see, if we plug in the Thevenin equivalent circuit to the base, as you see, from the ETH source, we have the current, base current, which is passing through bar RTH, and this is entering directly to our base. Great. So the voltage drops here, here, here. This is the base emitter voltage drop here, and RTH. Okay, VRTH. Okay, one thing here, U, C, E, Q is here. Okay, so first of all, let's find the base current according to this simple electronic loop, and let's build the equation for it. Let's say that we've got the clockwise direction, and what we'll have, ETH is positive, minus voltage drop on the RTH resistances. So this is the IB times RTH. Next voltage drop, we've got the UBE, or VBE, sorry, and the voltage drop on the emitter resistances, VRE. VRE, it is IE times RE. And everything should be equal 0 because the sum of the voltage drops in the closed loop should be equal 0. Yeah, so this is the first equation. We've got it. As you see, this is known, this is known, this is known. The problem is the current. However, we know that the emitter current, it is the IB times beta plus 1. So as you see, the ETH minus IBRTH minus VBE minus IB beta plus 1 times RE is equal 0. So we have to find the current IB. So the current IB will be equal, I move it to the right side, and it stay ATH minus VBE over, okay, if you substitute the IB before the bracket, I will have RTH plus beta plus 1 RE. Oh. Okay. So we've got it. Yes. Okay. ETH, it is how many? 3.53. That's right. Yes. Minus VBE 0.6 in our case. So this is equal. This is equal how many? 2.93 volts over the RTH. RTH, how many it is? 5.3 K plus beta plus 1. It is 100 plus 1. It is 101 times 820. No. 510 ohms. So it is equal around 51.6 microamperes. That's the beta. That's the current of the base. So in very quickly, we can find the IC current, which is equal beta times higher than base current. So it will be equal if multiplied by beta 100. It gave us the 5.16 milliamps. That will be the ICQ current. Great. And the last thing, we have to find the, according to some equation, we have to find the UBEQ. So as you see, let's choose this very simple branch, and the VCC minus voltage drop on the RC resistances, which is equal ICRC, minus UCEQ minus voltage drop on the emitter resistances. So this is the IE. RE is equal to 0. Great. So we have to find the ICEQ. And again, we know ICQ current, so IC is given. We know what is the beta. So it depends on us how we can calculate them. We can choose that form based on the only on the base current. IC, it is IB times beta RC minus UCQ minus IE, it is IB times beta plus 1 times RE. Great. So UCQ, it is equal. We have to move it to the right side of the equation, and we've got the VCC minus IB times beta RC plus beta plus 1 RE. That's enough. All right. And when we will substitute the any values, we will get 3.11 volts. So as you see, that's the one case, that's the one possibility way to find the DC and DC working point for this transistor with that type of base polarization. Okay, using the voltage divider. Great. As you see, the Thevenin methods is very helpful for us in electronic circuits, and calculations make so easy. Please try to find this results, in fact, based on the typical equations without the Thevenin theorem methods used here, without the Thevenin methods. Okay, great. So I think we can make some break because we've got the extra 2 hours. Yeah. I will try to using this where it is. Yeah. Jakub.
Yes.
I have a request. Could you send me again this website address on the chat at this moment? Because we make the new session, so I lost them.
Okay, but I think Wojciech. Yeah, I think Wojciech has better link.
Okay, VC. Oh, all right.
Yeah. This one is like official Polytechnica website.
Okay, so thank you again. So let's make how many? Maybe half of hour. Do you want some half of hour break?
Okay.
I don't know about others, but maybe it doesn't need to be that long. But I don't know.
Take your time to set this up.
Yeah, that's true.
Okay. All right. So we are making the break. I will try to solve the problem with the Zoom, and we'll be heard with by, I don't know, maybe 15 minutes, 20 minutes. We'll see. Okay.
Okay.
All right. So thank you. Okay, so the first question is, do you hear me?
Yes.
Yes.
Great. All right. So I promised you last time that I will show you how we can make the AC analysis for for the amplifiers based on the bipolar transistors. To this moment, we done the analysis for such a circuit. Okay, so first of all, before we are going to before we go, we will go to the AC analysis. You have to know how it looks like the model of transistor. So at this moment, I will give you, and please note it, I will give you some basic information about it. Okay, we've got a few types of models of transistors. For the bipolar one, for the low frequencies, it names like the hybrid pi model. How it looks? Yes, something was happened. Hybrid pi model. Hybrid pi model for the bipolar transistor. It looks like that. This is the base. This is the RB prime C resistor. This is the dependent current source. Here we've got the emitter. This is the internal resistances between the collector and emitter. And this is our collector. And here we've got the, RBE, resistances between base, between the base and emitter. All right, it looks like that. However, you have to know that this resistances between the base and the collector is so huge. Is so huge, some mega ohms. It means that we can approximate this this model by the open circuit between these 2 points, because the RBC is so huge. So that's why we can reduce this model to this one. All right, this is the first thing. So, in fact, if you see the transistor like that in electronic circuits, in fact, we can replace it by its model, which looks like that. Okay, so we have to, I have to give you some theory at this moment, but very briefly. The first thing, as you see, this is the current source, dependent current source, which depends on UBE. UBE, it is the voltage drop between the base and emitter, as you see, and some parameter here, GM. What is the GM? GM, it is the transconductance. And transconductance. the transconductance, it is the changes of the collector collector current over the changes of the base emitter voltages. This is for the conditions. This is for the UBE, of course, for some value, changes of the UBE. However, UCE should be constants. What does it mean? For these conditions, GM, it is equal Q CEQ. So this is the ICQ. This is the current. This is the collector current for working point, for DC working point, over phi t. The phi t. This is the thermoelectric potential, which is calculating like that. This is the Boltzmann constant temperature over Q, where the Q, this is the charge of electrons. No, the charge of electrons, electron charge. Okay, so how many the QT it is? For the room temperature, phi t, it is equal around 26 millivolts. So if you wanted to find GM parameter, the transconductance, in fact, we have to know what is the DC collector current for our transistor. As you see, it is not possible to make AC analysis before DC one. So you have to firstly you have to make the DC analysis and find the working point for transistor. That's why we have to make it at the beginning, and then we have to go. We can go to the AC analysis. So please remember, phi t, it is 26 millivolts, and GM is given by that formula. Okay, next thing. The RBE. As you see, this is the input resistances. This is the input resistances, which is here. This is the resistance between the base and emitter. From the definition, the RBE, it is calculating according to the Ohm law, changing of the UBE voltage drop over the current IB for, of course, UCE constants. Okay, so let's find what is the RBE. The RBE, according to this definition, it is changing of the UBE over the changing of IB. However, we know that the beta for transistor is given by that formula. IC, it is the beta times IB. So for the changes, I can write it in that form. Changes of the current IC, it is the beta times changes of current IB. All right. So the beta, it is changes of IC over the changes of IB. Look, let's play at this moment for some game. We've got the UB over IB, and let's try to let's try to add something for this formula, but we can change it, of course, to finding the RBE. Look, what we've got here, GM, it is the IC over UBE. We've got the IB here, but we haven't the IC, we've got the IB. So please imagine that the UBE over something times something here in the denominator divided by changing of the IC, current IC. I have to put it here the same values, the same parameter, and then I will not change the RB formula. But as you see, UBE over IC, it is GM. Yes, but in this formula, sorry, this is the IB. Sorry, this is the IB. I need put it here something and divided UBE to get known values like the GM. So look, if I will divide this this formula by the IC and multiplied by the IC at the same time, because I can change the RB formula, look what I have. What happened here? Oh, the sun is disappear. Okay, look, UBE over ICE, this is the reciprocal of the GM. This is the 1 over GM. IC over IB, as you see, this is the beta. IC over IB. So this is the beta. So RBE, it is the beta over GM. Okay? Do you got it?
Yes.
Great. Okay, next thing. I need paper. What we've got at the model, we've got the RC, the output resistances. Output resistances. Okay, RCE from definition, it is the changes of UCE over the changes of current IC for the UBE constants. However, the RCE, you can calculating from that formula. The early voltage value plus UCEQ over ICQ value. This is the early voltage. UA. And what is the early voltage? Please remember the expression or the function between the UCE and the current IC for the transistor. The shape of the functions looks like that, and this is for the different value of base current, and so on. If you will take the straight part of the any function, we will see that, and this part of it will be crossing here at the one point. And this point is named, it is the early voltage. UA. As you see, the UA, because this is the 0 here, UA, it is negative, it is the minus here. That's why this is the module here. And for calculations, of course, the early voltage is different for the different transistors. However, typical value for it, it is minus 100 volts for the bipolar transistors. So, as you see, we need the early voltage and the UCQ, which was calculating for the DC analysis, and the ICQ also to find the RCE. However, if you are operating for the low voltages, supply voltages in our amplifier, we know that UCEQ, it is not so huge. It is around the half of the voltage supply value. So if it is 4 volts and the UA, the early voltage is around 100 volts, it means the 100 is it's so much more bigger than UCEQ. So we can use the simple formula for the ICE, like the module from the UA over ICQ. Yeah. Why? Because UA, it is much more higher, bigger than UCQ. Okay. So as you see, we can use this formula or this one. Yeah. Okay. Because we haven't a lot of time to talking about these RBC resistances, I can tell you very quickly that the RBE from the calculations, from the definitions, it is equal beta times RCE. RCE, it is tens of kilos, hundreds of kilos ohms, and multiply by beta. Beta, it is 100, 100, 800. So as you see, what the value of RB is so huge. However, that is only the calculations. In real, you have to know that the RBE, it is around from 5 to 10 times higher than beta times RCE, because this is just the calculations. That's the real value. It could be around 10 times higher than this. So it is mega ohms. That's why we don't have to sorry. Sorry. In the hybrid pi model, we don't have to take it into account, this resistor. Why? Because here the current is really very, very low, under the microamperes. Great. So please note it, because this formulas is very important to make the AC analysis. Great. All right. So I think we can start. We can start the next example. Right. And in this example, we have to, the question is, what is a voltage gain and what is the voltage gain, sorry, effective voltage gain, the input resistances, output resistances, of the amplifier based on bipolar transistor. All right, how it looks like the circuit. This is like that. Okay, we've got it. Okay, do you hear me?
Yes.
Okay, so Zoom is working now. Great. The conditions for this example. RB1, it is 56 kilo ohms. RB2 is equal to 20 kilos, so kilo ohms. RC, it is the 6.8 kilos. RE, it is 3.3 kilos. RG, it is 1 kilo ohms. RL, it is 10 kilos. Okay. The beta for transistor, it is 200. And ICQ is given. Yeah. This is 1 milliamps. And the UCEQ, it is the 5 volts. Without these values, we will have to make the DC analysis according these parameters for our circuit, like previously, because this is it, in fact. And what else? We have to put it clearly early voltage like the minus 100 volts. Okay, that's enough. Great. So first of all, we have to and here we've got the capacitor also on the emitter. First of all, let's we have to assign where we've got the input and the output point for our amplifier. Where it is, where is the input and where is the output? Do you know where? The input is where? Sorry, again, please could you repeat it? VCC? No. This is the voltage supply for our amplifier. But where's the input input for the signal, and where is the output for our. Look, this is the amplifier. Any amplifier should be powered. Yeah. This is the input. This is the output. Yeah. Okay. So the input is here, and the output is here. All right. Great. Why in the voltage in the amplifiers the emitter resistor, which is used for thermally stabilize the amplifier, is paralleled with by capacitor with the huge value, because this capacitor has no influence for the DC analysis, yeah, because the DC signal is not passing through it. Yeah, this is the capacitor, of course, but this is the huge huge capacitance. So for the typical frequencies, like the audio ones, this capacitor has the very, very low impedance. So we can say that for the AC analysis, for the signal analysis, this capacitor, it is like the short circuit for the RE. It means that the AC signal don't see the RE resistances because it is short circuit by this capacitor to ground. Why? Because if we will not put it here, this capacitor, the AC signal will see the voltage drop on this resistor. What happened there? The voltage changed here will be lower. So it means that the output signal will be lower too than the situation where we will have this capacitor. That's the one case. Great. How we can solve it? How we can make this AC analysis? First of all, we have to redraw this circuit for AC signal. What does it mean? We have to take, first of all, we have to take the transistor and we have to replace it by the hybrid pi model, by this one. Okay, so let's make it. Okay, this is the base, and here we've got the RBE resistances, as you remember. This is the dependent current source, GM UBE. Here we've got the RCE, and this is the collector. And here it is the emitter. Okay. As you see, what I done, I just replaced the transistor by its model. And now for the AC signal, I have to connect the rest of the components. But we have to be very careful because the capacitors in this case it is like the short circuit for the AC signal because they have huge values. So this is one case, and another one, VCC, the voltage supply signal. This is the DC signal. What is, or how we can replace the VCC signal, VCC voltage supply for the AC signal? How it looks like? Look, if you have the power, the voltage supplier on the output, of course, it is destabilized. Yeah, the voltage is stabilized. it is stabilized, and we've got a lot of capacitors on the output, yeah, for filtering. So the question is, what the AC signal is can see here or observing according to the VCC terminals. There's a lot of capacitors here. It means, with the huge values, it means that the AC signal, for the AC signal, this capacitor is like the short circuit. So the AC signal, in fact, see that the VCC potential, it is like the short circuit to the ground by these capacitors. All right, so if we know that, we can go further. Okay, we've got the collector here, base and emitter we've got here. And from collector, as you see, I see that we've got the RC resistances, which is connected to it. And look, the second terminal of the RC, it is connected by the VCC to the ground, yeah, because AC signal is the short circuit between the VCC and the ground. Okay. From the collector, I see that I have a junction, which is going to the capacitor. So from the collector, I see the junction. Here it is. And I've got the capacitor, but the capacitor, it is short circuit for us. And then I see that I have the output terminal. And then from the output terminal, I see that it is connected by the load resistances to the ground. Great. What about the emitter? Emitter, it is connected by the capacitor to the ground. So, in fact, the emitter is short circuit to the ground directly. So AC signal don't see the RE resistances. So the emitter is connected to the ground. What about the base input? The base is connected to the two resistances, as you see, RB1 and RB2. RB2 is directly connected to the ground. RB1 is connected to the ground by the VCC point. Okay. Great. And also the base here is connected to the input terminal by the capacitor, which is, for us, it is short circuit. Great. And what else? I've got here the RG. RG, this is the internal resistances for our generator or the input signal source. Let's say it like the EG. All right. So as you see, that looks like our electronic circuits, which is here, for AC analysis. Okay. So for this moment, everything is clear. Maybe yes. Are you still there? The Zoom is working?
Yes, it is.
Okay. Great. So one thing here, because we have to find the voltage gain and effective voltage gain. What does it mean? Sorry. The voltage gain, Ku, from definition, this is the V out over V in. Yeah. So if you have the input voltage equal 1 volt and on the output we've got the 100 volts. It means that the gain, voltage gain of our amplifier, it is 100. Yeah. So this is from the definition. Where we can observe the output and the input voltage for the signal on its terminals. So here it is the V out, and here it is the V in. Do you see it? So, in fact, between these 2 points, we can calculating the voltage gain. What is the effective voltage gain? The effective voltage gain, it's take it into account the internal resistances of the signal, of the source signal. Because the effective voltage gain, sorry, this is the Polish notation, sorry for that. This is the V out over, what do you think? Over what? Voltage, the output voltage from our source, e.g. Why? Sometimes maybe you have the situation where you have, when you have the generator, yeah. And please tell me, I don't know, do you have some laboratories? I think yes or not. Aha, yeah. Sorry, we have the pandemic. Sorry. Okay, so you don't see the generator, in fact, in real. The generators has some output impedance, yeah, and typically this is the 50 ohms or 600 ohms, but typically it is 50 ohms. What does it mean? If I put, or if I set on the generator voltage value equal 1 volts for the sine waveform, so I set the EG value. However, if I know that the output resistance or impedances for our generator, it is 50 ohms, and this is our output terminal, and here I plug in, for example, I don't know, scope or something like that, which has some resistances here. Let's say this is the also 50 ohms. Let's say that one. Please tell me what the voltages for the AC signal, of course, will be observing here.
Half of voltage.
Yeah, it will be half of volt. Yeah. Why? Because we've got the voltage divider due to that the output resistance of the source signal exists here. So that's why it is very important to know what is the input resistances of our electronic circuits or and else what is it, because if we plug in it to our generator, we'll see that we haven't the 1 volt, we've got the half volts. What happened here? Yeah, so that's why it is sometimes it's very important if we wanted to connecting, for example, the stages of the amplifiers to get the minimal, very low, the output resistances, yeah, and very huge input resistances of our, for example, amplifiers. Why? Because then, if we have the 50 ohms as the RG here, our input resistances for the next stage, for example, of the amplifier, it is not the 50 ohms. It is so huge. Let's say it is 1 mega ohms. What will be the input voltage for such amplifier with so huge impedance? It will be, we can say, almost 1 volt. It will be maximum. It will be maximum. That's why when we talk about these transistors, and you said that the JFET transistor was, you said that JFET transistor is commonly used for the RF signals, yeah, for the RF circuits. That's true, of course, because they have the huge bandwidth. And then I told you that they have the input, very huge input resistances on the gates. So that's why. Great. So let's coming back to our circuit. And that's the differences between the voltage gain and effective voltage gain. The first one, we have to take into account what is the real input voltage which is connected to the input input terminal of our amplifier. Yes, and the effective voltage gain. In fact, this is the voltage which is calculating, which is take it into account the internal resistance of the source. Okay, so let's make the calculations. I need some, here it is. Okay, so first of all, I told you that let's calculating the for example, the effective voltage gain. The typical voltage gain, as I told you, this is equal V out over V in. Yeah, we've got it. V out over V in. The effective one, it is the V out over EG. The value which is set on the generator, the signal, or on the signal. So the question is, we have to change this formula like previously when we talked about the parameters of the, where it is, of the, for example, RBE resistances. Yeah, I made some quiz here, let's say, yeah, and the question is, let's find this value, changing the typical formula by adding something new, but we can change it. In fact, this formula can be changed based on the previous values or known values. Look, so in fact, this is some kind of quiz here. Great. This is the V out. Okay. The question is, if we've got the collector here, and we've got the V out here, as you see, the RL for the AC signals, of course, the load resistance RC and the internal RCE resistances are connected, as you see, in parallel. That's right? Yes? So we'll have, how many is the voltage drop on in this case? The output voltage will be equal the current, IC current, which is divided by these three resistances, yeah, and the parallel connection between them times IC gave you the V out, yeah, using the Ohm law. That's right. That's right. So let's write that formula. V out, let's divide it by something to get the values what can be possible to find. Let's divide it by the IC here. Why? Because it is possible to find them, because we know that it's parallel connection between the resistances. Okay, if we divide it by IC, we have to multiply it by IC, yeah, because then it can be reduced, so we can change the beginning formula. All right, but what we have to put it here to get some known values. What? Sorry, I forgot about something. What is the V out over IC here? This is the total resistances here, which consists of 3 resistors. That's right. That's right. So this is like the R total, in fact. Okay, so I know how to calculate them. R total. What is the R total? It is the parallel connection between these 3 resistances. Yeah, V out over IC. Great. Next thing. We've got the EG here. Okay, we've got the IC here. We have to put here the same values, the same parameters to get some known values like this and this. Do you have some idea? Okay, no. Great. So now please take a look at the transconductance parameter, GM. From definition, what is the GM from definition? How we can calculating the GM from definition? What is it? Please tell me.
IC divided by phi t.
IC divided by?
Phi t.
No, but I mean the definition. From definition, GM is equal?
Change in momentary current divided by change in voltage.
Yeah, or for the fixed value, it is the IC over UBE, yeah?
Yes.
Okay. We've got the IC here. Let's divide it by UBE. What is the UBE? This is the voltage drop between the base and emitter, yeah? UBE. So emitter here, it is on the ground. So this is the UBE. But look, the base, to the base, we have the connection, the parallel connection of the resistances to the ground. And as you see, look, VBE, in fact, this is the same voltage drop like the V in. Do you see it? Yeah?
Yes.
Yes, of course. Look, UBE, it is the same like the V in. So I can change this UBE by V in. Okay. So here, let's put it here, the V in, yeah, because we have to divide it and we have to multiply it at the same moment, yeah. We can change it. And what we've got here, IC over UBE, in this case, UBE, it is the V in. In fact, this is the what? GM. Look, this is GM. The question is, what is the V in over EG? Look, what we've got here. This is connected to the ground. This is the V in. Do you see here some voltage divider? Look, these three resistances, the input resistances for our amplifier is connected in parallel. That's right. So we can change it to the one resistances, which will be looks like that. This is the V in, and here we've got the RG and our signal, EG. Do you see here the voltage divider? Yes? I think yes. So the V in over EG, the V in is the voltage on the input resistances. This is the parameter, which is called like the gamma U. This parameter tell you how we used, this is the coefficient, tell us how we used the input signal, in fact, according to the EG value. It means, in other way, what is, in fact, the coupling between the EG and V in. Yeah. Okay, let's calculating, or maybe that form. Let's show on the or indicate the input and output resistances of our amplifier. So from input terminal point here, we've got the input resistances for our amplifier. And also from this point, from output terminal, we've got the output resistances. Yeah, that's right. That's right. Great. So using this, using the formula for the voltage divider, we can write here that the V in, it is equal. Please tell me. This is just the voltage divider. So please tell me what is the value of V in? How we can calculate them?
IG.
Yeah. Times.
R in.
Yeah.
By R in plus RG.
Great, of course. And look, if I will divide it both sides by EG, I've got the V in over EG, which is equal R in over R in plus RG. And in fact, V in over IG, it is gamma U. Okay? Great. Look, one thing here, it is not clear. Look, the voltage drop here, it is going up. Yeah. So the current IC should passing through in that direction. That's right. However, in fact, we've got the current source here, which has the opposite sign. Why? So the question is, what do we have to do? What do we have to do to get that direction of the current? What do we have to do with this dependent current source? What do we have to put here something to get the opposite sign of the current flow.
PNP?
No. We have to make that the GM is negative. That's right. This is the minus GM. Then the current is passing through in opposite way. That's right. Yes. Yes.
Yes.
So why we have to put it here the minus GM? As I showed you on the previously on the LT Spice, the simulation of this PNP based amplifier, you will see that the phase between the input sine waveforms and the output one is shifted by 180 degrees. Do you saw that? Do you saw them? Did you saw them?
Yes.
Yeah, that's right. So as you see, the amplifier in configuration with the common emitter, as you see, the common emitter here is connected to the ground. They shift the output phase signal by 180 degrees according to the input signal. That's why here we've got the minus GM. And this minus tell us that not the negative value of GM we've got. No, that this minus tell us that the phase is shifted by 190 degrees. All right? Great. Sorry. Next thing. What will be the at this moment you can say that effective voltage gain, it is the total output resistances times minus GM times gamma U. Okay. What about the voltage gain? Typical voltage gain, it is like the V out over V in. So of course we have to make some quiz at this moment. We've got the V out. Okay. And this is the V in. Great. So the question is, what we can put it here, the same values, the same parameters, to calculating something which is given, in fact, in our circuit. So as you see, this is nice quiz, in fact. Okay, so what will happen when I will put it here, the IC, current IC? What I've got, V out over IC. That's right. What is the V out over IC according to the Ohm law? This is some resistances, yeah? What is it? V out, here, it is here. Voltage drop on each resistance is connected in parallel. The IC, it is here. So V out over IC, it is the total resistances, total output resistances, total. If I divided the formula by IC, I have to multiply it by IC. And again, look. And again, IC over V in. But please start to thinking. Look, Vin, it is the same like the UBE. Yeah. So it is in fact here it is the UBE. What is the IC over UBE? It is here. Look, from definition, IC over UBE, it is GM. That's right. That's right. This is GM. Of course, we have to put it here the minus because the current is in opposite way. Look what we've got. The voltage gain, in fact, this is the RT times minus GM. The effective voltage gain, it is the RT times minus GM times gamma U. So, look, RT times minus gamma minus GM. In fact, this is the KU. So, the effective gain, it is the same like the voltage gain times gamma U. Do you got it? Please don't be scared, of course. This is just for you. This is something extra from me. I don't think so that I will give you such examples on the test. Don't be scared. A little bit, yeah? Yeah, but that looks like the electronics, in fact. It is not so easy, as I said on the beginning of this course. Great. However, I show you that it's possible to find it. Yeah, we have to just start to thinking, and I think the best way to learning something, it is first of all it is example. If somebody gave you some example and he tell you what you have to do, then you can start to thinking much more better, I think, because you know you've got something in your head that somebody's told something about it, yeah, somewhere, yeah, and then you can connect some facts and then solve the problems. Great. So we can coming back to our example and make the calculations. All right. So did you note everything?
Yes. Yes.
Great, great. All right. So first of all, we have to calculating, for example, I don't know what will be the first one. Doesn't matter. KU. KU, it is the RT times minus GM. So first of all, we have to find the RT. So the RT, it is equal. And let's coming back to our circuit. RT, it is the total output resistances which take it into account the load resistance. That's right? That's right. So this is the parallel connection between these three resistances: RCE, RC, and RL. Okay. RC we've got, RL we've got, we haven't the RCE. Of course, we have to find the RCE. As you remember, sorry. I hope that this is not the coronavirus. The RCE can be calculating from that formula. Early voltage plus UCEQ over ICQ. Yeah, it can be calculated in that form. So please, so we can calculate it very fast. How many it is? This is the minus 100 volts plus 5 volts over 1 milliamps. So this is 105 over 1 milli. As you see, this is 105 kilo ohms. Look, RC is equal 6.8 kilos. RL, it is 10 kilos. RCE is 105 kilos. So in fact, this resistor has no so huge influence for the RT in this parallel connection. Yeah. However, we can calculate it. Okay. So very fast. This is the 105 kilos times RC. RC, it is how many? RC. 6.8 kilos. Yeah. It is equal like that, divided by sum of it. 105 K plus, I don't know, 6.8 K. So these two resistances gave us, in fact, 6.39 K, which is parallel with the RL. Okay, I had to remember this result. RL, it is 10 kilos. Yeah, that's right. So this value times 10K, it is equal like that, divided by sum of it. So this is the 16.39K. So in fact, this is around 3.9K. That's the RT. We've got it. Next thing, we've got the RC. Yeah, we've got the RT. Okay, we have to find the GM. GM, as you remember, it is equal ICQ over phi t. Yeah. So it is equal ICQ. It is 1 milliamps over 26 millivolts. Yeah. This is this potential phi t. So 1 milli over 26 milli. It is 0.038 Siemens. Okay, that's the transconductances. Okay, I have to write it in on the F for me. Okay, we've got the GM. So we can find what is the voltage gain here. This is the RT times minus GM. So this is 3.9K times minus 0.038. So this is equal F times 3.9K. Look, 150. As you see, there's no, this is the Siemens. In fact, the KU hasn't the unit yet. Why? This is the Siemens. The Siemens, it is the reciprocal of the resistances. This is resistances, so resistances will be reduced. There's no units here. However, we know that this is the V out over V in. So this is the volt per volt over volt. What does it mean? If you will have 1 volt on the input, like the V in, yeah, this is 1 volt. So this amplifier will gain our signal by 150. It means we should have as the V out equal 150 volts. It is possible. Please tell me.
If we supply this voltage and choose correct transistor?
Yeah, that's right. Yeah, Jakub, you have right. It is possible. However, we have to supply our circuit not by 10 volts for the VCC, because if you have the VCC equal 10 volts, it is not possible to get higher output signal than 10 volts. Yeah. But we have to remember, you have right, we have to choose the correct transistor, which will be not broken for so huge voltages. Yeah, that's right. So you have to remember the limitation. The limitation of the output signal for amplifiers, it is the VCC. Great. Very often, the voltage gain or effective gain, and anytime the gain is represented by the decibels. Yeah. So how we can find this gain? What is this gain will be equal in decibel scale like that. We can find them in decibel scale like that.
Excuse me.
Yes.
What about this minus from GM?
Yeah, of course we've got the minus here, but this minus here is not show you that we've got the gain equal minus 150. Yeah, because if it will be true, we'll have the amplifying of the signal. It will be attenuating. That's right. I told you that this minus here tell us only that the output signal is shifted by 180 degrees according to the input signal. All right. So we don't take it this minus like the value, like the sign of the value. This minus indicates that the output signal is shifted by 190 degrees according to the input. All right.
Okay, thank you.
Because this is the common emitter configuration of the amplifier based on the transistor. So, in fact, this is the 150. So we've got the amplification here, not attenuation. Okay, so Q in decibels. Yeah, that's right. I see it. Yeah. Yeah, this is the minus, of course. Yeah, but this minus show us that, or tell us only about the phase shifting. Okay, for the voltages, currents, the formula, it is like that. It is 20 logarithms with the base of 10 from V out over V in. If the V in, it is 1 volt, so we are considering the decibels according to the 1 volt of the unit. It is simple. So this is 20 logs 10 from V out over V in, it is Ku from 150. So it is the, where I have got the logs here, here it is. Logs from 150 times 20. As you see, this is 43.5 decibels. We've got it. All right, so let's calculating the effective voltage gain. Effective voltage gain, it is equal RT times minus GM times gamma U. As you see, RT times minus GM, it is the Ku, in fact. Yeah. So we've got it, the Ku is given at this moment. So it is the Ku times gamma U. So this is 150 times gamma U. So we have to find the gamma U. Gamma U, it is equal, as I told you previously, this is equal Rin over Rin plus Rg. This is just the voltage divider, in fact, on the input. Okay, we haven't the Rin. We haven't got. So Rin, it is equal. Please take a look at the at our AC circuit. Rin, so we have to take it into account only the everything what happened after the input terminal. As you see, RBE is connected to the ground. So the question is, what is the Rin here? It will be equal what? The parallel connection of these three resistances, RB2, RB1, RBE. Yeah. We've got the RB1, we've got the RB2, but we haven't the RBE. But if you take it, take a look at the expressions for the transconductance, input resistances for the resistor, for the transistors, the RBE, we talk that the RBE, it is the beta over GM. Yeah, that's right. Yeah, so the beta is 200. The GM, it is 0.038 around. So 200 over GM, it is 5.2 K, 5.2 kilo ohms. Yeah, so we've got it. What else? So we have to find the Rin. All right, let's make it. First of all, let's calculating the RBE parallel with the RB1. RB1, it is 56 kilos. So 5.2 kilos times 56 kilos. Yeah, and we have to divide it by how many times? It was 56, I think, kilos plus 5.2. So it is 4.76 kilos around, and then we have to calculate the parallel connection with the RB. 2. Okay, I'm just storing it on the B. Okay, and the RB2, it is 20 kilos. So this one times 20 kilos divided by this one plus 20 kilos. Okay, so this is equal 3.84 kilos. That is the input resistances of our amplifier. So that value C, the signal which is coming to the input, right? So now we can calculating the gamma U. So it will be equal 3.84K over 3.84K plus 10K. Okay, as you see, the gamma U, it is 0.28 around. Yeah, of course there is no unit here. So coming back here, we've got 150 times 0.28, and this is equal 42. 42 volts per volts, over volts, sorry. So as you see, if we'll build such circuit of the amplifier, and we'll have the signal source like the generator with the input with the output resistances Rg equal 1 kilo ohms, and we set our signal generator on the 1 volts. On the output, we will see the signal which is gained by 42 times. So we'll have the, how many? 42 volts. Do you see the differences? Look, the same amplifier has voltage gain equal 150, but effective it is 42. Yeah? So as you see, if I will ask you, I know that KU for our amplifier it is 150. I set the EG at 1 volt. What is the output voltage or gain voltage? Many students will tell 150 volts. No. Why? Because in fact on the input we've got the voltage divider here. Yeah, voltage divider, and you have to remember amplifier is amplified. In fact, the input signal here, this voltage is amplified, this one by 150 times. Yeah, right. So as you see, this gamma U parameter, we can say this is around the 28%. The gamma U tell you what part of the input signal, in fact, on the generator is going to the input of the amplifier. So in this case, only 28% of the 1 volt will be appear here like the input voltage according to this voltage divider, and this voltage is amplified by 100 times. We can check it. Look, 1 volts times 28%, 0.28. It is, of course, 280 millivolts. And this voltage is amplified, and this voltage here is amplified by 150. So times 150. Look, 22. In fact, we've got the 22 volts on the output. That's true. That's true. And the last thing, what is the gain? 22 gain. It is for in decibels. It is 20 logs from 22. It is 32.5 around decibels. Okay, that's the gain here. 42 times, and this is in decibel scale, 32.5 decibels. Okay, great. So that's the everything what I prepare today. As you see, it is not so easy. However, in fact, you can learn. You can learn, and I know that you are so you are good students. So I don't think so that you will have much more problems with understand it. However, today I gave you so many knowledge, I think. So if you make if you done some notes, please on the evening or for some few hours, please take a look at again on the notes and please try to understand it again. And then you will see that this is not so difficult, in fact. Okay. So thank you again for today's classes, and in the next week we will starting with Laplace transform. I think. Do you have the Laplace transform on the lectures with Adam Vaughan?
Yes.
Great. Okay. Great. What else? Anytime when I have the classes or lectures, especially classes, I see that the people which is connected by Zoom to teaching the classes or teaching the electronics on the classes, it is around 55. Not 55, 25. Yeah, 20. Yeah, 25, 28. Sometimes at the end, at the beginning of the Zoom this webinars, it was 38 as the maximum. I know that at this course, at total is 51 or 52 two persons. So I worried about the rest of the people. What happened? Why they don't want to? I don't know. Connecting by Zoom and teaching. So I don't know that Julia is connected today. Where I can choose it. I can see the Julia today. That's right. The Camille, yeah. However, you mean that they have some other courses? Camille? Or the whole? Aha. Of course, yeah. I understand it because, of course, my child also are at home, but I think if you have the lectures, so yes, okay, Camille. Yeah, maybe yes. However, if you have you are not at the home, like at the holiday, not on the holiday, but you are studying. So I don't think so that it is enough for stop to learning. Okay. Please tell me, because we've got the two groups, in fact, on the classes. Sometimes the people have the classes on the Tuesday and the Thursday. That's right?
Yes, that's right.
So my question is, because I don't think so that it is a good idea to make this, because this is the online, everything is online here. It is making the same in fact classes for the first and second group. Yeah, please tell me, there are any students from the Thursday group at this moment? Or everybody are from the Tuesday group?
I don't really remember which group I am in at
Okay.
this point. But yeah, I'm from the Tuesday group, so I don't know the others.
But there are some students at this moment are connected. There's some students at this moment which has typically the classes on Thursday. So please tell me, do you have some at this time when we have on the Tuesday classes? Do you have at the same time some other lectures on classes? Great. Okay, that's enough. Because I'm just wondering. I'm not listening. Too bad. Because I don't want to have the situation that some people at the end told me that, oh, I don't know that we've got the classes at the Zoom. It was on Tuesday and something like that. Yeah. So because you haven't the any classes or any other, I don't know, lectures or something like that on Tuesday during the classes from electronics time. So that's why I sent by email the information about Zoom meeting to everybody. So everybody should connect to this course and listen it and observe everything. Yeah, Camille, I think yes, you have right that this is enough. However, please believe me, sometimes the students have so huge imagine. Yeah, me wash, yeah. Nothing else at this time. Yeah, that's right. So okay, great. Whoa. So thank you again. If you've got some question at this moment, please, you can ask me if you want at this moment. If not, do you have some questions?
Yes, I have. About this effective
gain.
Gain. Yes. So if wouldn't if we put here voltage follower, wouldn't that solve?
Sorry. We put here what?
Voltage follower from operation amplifier.
Operation amplifier here. Yes.
Yes. Voltage follower.
Yeah.
You know what I'm talking about.
Yeah. So.
Yes. So on output of that amplifier, it is low impedance.
On the output, yes.
Yes. So we would have a higher effective gain.
Yeah. Yeah. Of course, because everything, in fact, depends what will be the input impedance for your amplifier here. Yeah. That's why we are going to get the maximum input resistances according to this voltage divider here. Yeah, you have right. So what we can do here to get much more higher effective voltage gain, we have to increase the input resistances. However, look, even the RB2 and RB1, it can be chosen by us, yeah, during the designing process. The problem is with the RBE, the input resistances for of the transistor. As you see, we are calculating the RBE at the level of, I have to check it, where it is. Yeah, look, 2.5 kilos. Yeah, of course, it depends on the beta. So the question is, if you will replace the transistor with higher beta, like 800s, over the 0.038, because it is look, we've got the 21 kilos. So as you see, at this one, you can see how many ways we've got at this moment to increase it, to change it. So first of all, transistor, the beta. But the question is, if you will have 21 kilos of RB, yeah, so this is our limit, because we've got the RB2 and RB1. Even the RB2 and RB1 will be so huge, mega ohms. The input resistances will be equal almost 21 kilos. So RBE determines the input resistances, as you see. The RB2 and RB1 are decrease this input resistances. But at this moment, you can see, even we'll have the 21 kilos, what will be the phi, what will be the gamma U value? It is 21 kilos over 22. Look, it is enough to get, look, 0.95 of gamma U. It means that that 95% of the EG signal, it is going to the input. No, it is better.
That's quite a drastic change.
Yeah, this drastic. Yeah, that's right. So as you see, only you have to just replace the transistor and use it with the higher beta. So it should be not the, for example, this transistor with the C letter at the end of the symbol. Yeah, for example, B, C something, and C at the end. Yeah, that means that the beta should be around 700, 800. That's the one one case. Another, it is choose correct the resistances. However, in fact, the limitation is here.
And I also see that it depends on this GM, and GM is collector current divided by input voltage. So if you would decrease collector current, you would also increase effective gain.
Yeah, because the GM is going up, yeah? However, we'll have to calculate it, what will be the change for the effective gain when, for example, the ICQ current will be going from the 1 milliamps to 10 milliamps, yeah? It will be 10 times, yeah? That's right? Yeah?
Not too.
GM will be higher than 10 times, yeah? If you will change the ICQ current from the 1 milli to the 10 milliamps, yeah?
Yes.
Yeah, that's right. So we'll increase the voltage gain and also the effective gain, yeah? However, as you see, the crucial here, it is gamma U, in fact. Even you increasing the KU, yeah, by GM, the gamma U will stay at the level of 0.28. So as you see, the much more better it is change the transistor with the higher beta.
Good, thank you.
All right. So thank you again, and we'll see in the next week on the Tuesday. But I have got the big request, especially for the Julia, but it is not Julia, but it is not present at this moment. So my request is to write some email by the Julia to the students about this course. I mean, I think she should write the information that the classes on the Zoom is working. We are teaching, yeah. So we are studying. So I think they should, the students should connecting by the Zoom with this